All right, here we go. Let's talk about pee. What did you, what? The computer said you had a big head? You know you got a big head if you're working on the computer and your error message pops up. I'm afraid that your head is too large to work at this station. Okay. All right, talking about the kidneys. Huh? I'm finished. I finished respiratory. Yep, we're in the kidneys now. Whenever you're ready. The test is still Friday, so whenever you're ready. The kidneys. Now, you will find that, pass it. If you have your printouts done, pass them in and over your immunology stuff. We've got a lot to deal with here. The kidneys is I guess. There's a lot going on there. It's more than just like a coffee filter. It's not like they just filter out stuff and that's it. There's a lot of osmotic stuff going on here. There's some hormone control stuff going on here. We've got to address these issues. At first, I don't think there's going to be a problem. I think it's pretty easy to follow. The last few slides is where, when we start talking about specific controls of water balance and stuff like that, is where it gets a little hairy. But we'll do our best and try here. Okay, so as far as what they do, obviously everything that we're talking about here has to do with maintenance of homeostasis. Now, what is this? Did I give you this copy? Oh, good. Okay. All right. Yeah. Okay. You should know, obviously, that we're dealing with the biggest thing probably that we're all familiar with the kidneys is maintaining salt and water balance. Okay. Controlling how much sodium, especially, but sodium and potassium stay in and out of the blood, and as a result, remember, when you control sodium levels, what you end up controlling is water levels, because wherever the sodium goes, it's going to create an osmotic gradient. It's going to cause the water to follow it wherever it goes. Okay, so that's how we're going to control, for example, one thing, blood pressure. It's going to allow us to put more water in or take water out of the blood vessels, and that is going to help control blood pressure. Electrolytes are the things like sodium and potassium that we've been talking about. So here's a lot of other things that we're going to see that the kidney is able to function with or help control. Osmolarity, concentrations of sodium, potassium, that kind of stuff. Plasma volume, in other words, which will in turn affect blood pressure. Acid-base balance, you'll see that the kidneys can pull out or keep in hydrogens. When we talk about fluid and acid-base balance in one of the upcoming chapters, we'll talk about acids and bases, what they are, but realize acidity has to do with hydrogen. Okay, so if something donates hydrogen very easily and gives it off, it's an acid. So acid-base balance, and it's going to be controlling hydrogen ions as a result to control that. Obviously, waste excretion, foreign compounds, drugs, medication, leftover products, that kind of stuff. Also, you're going to see it's going to produce erythropoietin, which is helps cause red blood cells to be produced. Okay, that's something that will be secreted and induced by the kidneys. Renin, we will talk about, is going to be a hormone that controls blood pressure. There's a complex system that comes about because of that. And then vitamin D. It can actually take vitamin D and convert it into an active form. Do you remember what vitamin D does? Good. It helps absorb calcium. That's right. That's why when you buy the milk that's fortified with vitamin D, so it can get more calcium from the milk that you drink. Okay. This you should already know. You should already know the basic anatomy. With kidneys, you've got a renal artery and a renal vein coming out of the kidney. Renal artery going into it. You should know that the renal cortex, if you did it even if you cut open a pig from 102, you could bisect that kidney to front and back and see these where these lines are, where the cortex and the medulla are. But the cortex is, if you cut open the kidney, This outer layer right here, and the medulla is the inner layer right here before you get into the renal pelvis, which is sort of the drainage area here. So we've got this area, the pelvis, this, and this. Now within the renal medulla, you see these little lined areas called renal pyramids, sort of like funnels almost, where these nephrons are going to collect, and I'll talk about all these nephrons and what all that is in a minute, but the stuff sort of starts to collect and feed into what's called the renal pelvis, which is this down here. Okay, now obviously what comes out of here is the ureter, feeds out from the renal pelvis, one coming down both sides, go into the bladder to the urethra, urethra to the environment. Okay. Okay. The nephron is the functional unit. So it's sort of like when we talked about muscles, we said the sarcomere was the functional unit of muscle. That's basically, if we look at it, we know how muscle works. This is the functional unit of the kidney. Okay, these little nephrons. There's millions of these things in each kidney. What you're going to see, and I'll show you where they're located here in a second, but this part up here, okay, this is sort of, here's the bloodstream coming in, and it makes these little tufts, those little sort of like little wads of capillaries there that branch out into a whole bunch of little ones, like a little ball of them all together, so that it can increase surface area. And what's going to happen is there's going to be like a little cup called Bowman's capsule right here. This is a kidney tubule, a nephron. It's going to encapsulate that, go around it, and that's going to be the interface between the blood and these tubes that are inside your kidneys. And there's going to be passage of material through this into there, but there's also going to be, as you can see, when it goes in here and it circulates and comes back out, we've got afferent, we've got efferent coming back out. When it starts to come out here, it makes what's called a vasa recta, which is all of this, well, vasa recta is technically down here, but this whole apparatus that you see is sort of like a whole bunch of, a mesh of blood vessels all around and surrounding this tubule. It's all interwoven together. You can see that up here. And there's going to be a lot of communication. There's going to be a lot of stuff moving into and out of this tube and those blood vessels. There's going to be a lot of crossing. That's what we're going to look at, and what drives that, and all the stuff that goes on, and why that's so important. I mean, kidney failure is a huge deal. It means life or death in a lot of cases. So we need to see what's going on here and get a better appreciation and a better understanding of how this works. Because there's so many things body-wide that could feed into this and could cause this kind of stuff. Okay. Already talked about this. Okay, so we've got a vascular component and a tubular component. And that's pretty easy to deduce which is which up there. Big yellow thing's the tubular component. What you will see, notice I have labeled right here cortex and medulla. Where you're going to find these things are actually spanning from the cortex down into the medulla. This top part, especially what's called, remember your anatomical terms, proximal and distal, right? Proximal is like, if I had my arm out, proximal is closer this way and distal is farther away. So proximal and distal in this respect is in reference to the location from the Bowman's capsule. So when I say the proximal convoluted tubule, convoluted means folded, or I could also say just proximal tubule. I'm talking about this part of the tube right up here. Okay, the part that goes from here, winds all the way around and up, and down to here, that's all still considered the proximal tubule. And then once you get right here, someone said a minute ago, you probably already learned, this is called the loop of Henle. Okay? This loop of Henle actually starts to protrude down into the medulla. This part is in the cortex. It'll dip down into the medulla, come back up, the descending, the ascending loop of Henle, and then when it starts to get all windy again right up here in the cortex, that's called the distal tubule. Okay? And then it all feeds back into what's called a collecting duct, which will drain. Notice there's a bunch of feeds on this collecting duct coming from other nephrons that are nearby and around. Okay? All right. Now, we've got the glomerulus, which is that little tuft of capillaries that I was talking about that sticks into the Bowman's capsule. There's going to be filtration. And what you're going to see is a little bit, like with a coffee filter, that there's granules on the top and the heat and sort of steam makes everything get kind of runny and passes through those pores and leaves a solid particulate matter behind. This is similar to that, but what we've got here is also pressure worked in with this, because it's sort of like you're squeezing it. Not only are you letting it pass over a membrane, but you're applying pressure behind it and squeezing it and forcing it through there even faster. Okay? So that's what you're going to see. And you're also going to find that the capillaries here in this glomerulus those capillaries are actually more permeable. than normal capillaries in the body. Now, obviously, there's a lot of things that can go wrong. If for some reason they become too permeable, you can see there's a big problem because things are going to escape and get into the urine they're not supposed to be. Your proteins, your plasma proteins, your red blood cells, these are things that should never leave the blood supply. They should never be in any of the urine, any of the stuff that's collected in these tubules. If they are, you've got kidney problems. You've got permeability problems, especially. Like blood is a big one because those are big cells that actually have to get in there, blood cells. And if they've got that much permeability, there's some pathological conditions that we've got to deal with. Okay, I talked about this already. What's feeding into the glomerulus is the afferent. Remember, advancing towards, just like we talked with nerves. The afferent arteriole takes it into the glomerulus. After it goes through that little push-out filter, whatever's left comes back out through the efferent. Okay, the afferent arteriole. We've got paratubular capillaries. That's just another way to say capillaries that are around those tubes. We've looked at all of those, that big mesh and the capillaries that go around it and in it and everywhere else. Again, communication between the nephron, which is all that tubule network, between the nephron and the blood. Okay, that's where all this communication is happening. Okay. Notice here where I said, here's the cortex up here. Here's the medulla. I told you part of it dips down in. You'll find what's called cortical and juxtamedullary nephrons. Big words. All that means is, juxta means sort of positioned next to. Like juxtaposed, you put two things next to each other. Juxtamedullary means it's next to the medulla, this nephron. It's closer. In other words, most of its component is closer to the medulla. You'll find that in a cortical nephron, they're just named not because of the functional difference so much as just to where geographically where they are located within that kidney. That's all. That's the only thing that is really necessary to know about any of this. Okay, so again, just to review, we've got blood coming in through an afferent arteriole into the glomerulus. It gets sort of pressured out and filtered out. Some of it's left. It doesn't filter all of it, obviously. You can't get it all. So some of it comes right back out and keeps going. And it'll continue to wrap around all this tube as it's going. Some of it does get pushed through. A filtrate is what we call that, which gets pushed through. And it starts to collect, and it will travel through. This is the Bowman's capsule, proximal tubule, descending and ascending loop of Henle, distal tubule, collecting duct. That's the order. Okay? All right. Now, what does all this mean? Now we're going to be looking at filtrate. The stuff that actually makes it through, gets filtered from that glomerulus, the blood that's in there, passed through into the Bowman's capsule. All right. It says the three basic processes of the nephrons are glomerular filtration, pushing stuff past the glomerulus, however you want to say it, tubular reabsorption, and tubular secretion. Now, I want to point out something about this reabsorption and secretion because I'm going to say this often. I'm going to be using these words. And so you don't get lost, it's best to have a solid understanding right now of what direction I'm talking about. Okay? Because there's two different tubes here, and when I say I've got tubular reabsorption, what might want to pop in your head is you think of this as the tube, and if I say reabsorption, you're thinking of bringing stuff up into that tube. And that is wrong. Okay? When I talk about reabsorption or secretion, my reference point is the bloodstream. Okay? So if I say tubular reabsorption, I'm talking about bringing stuff out of the tube, absorbing it into the bloodstream. If I say tubular secretion, I'm talking about taking stuff that's in the blood, secreting it back into the tube. So make sure you understand that so that you can understand what I'm going to say. Yep, just like you see right here. This stands for tubular reabsorption. This stands for tubular secretion. See where the arrows are going. Okay? Reabsorption by the blood. From the tube to the blood. Secretion, secreting from the blood to the tube. Just realize the blood is your base. That's your reference point here. So if I say reabsorption, I'm talking about the blood's absorbing something. It's going to be absorbing it from the tubule. If I say secreting, the blood's going to be secreting something. It's going to be secreting it into the tubule. Okay? All right. So here's what we got. Notice, like I said a minute ago, here's our Bowman's capsule. I say GF, that stands for glomerular filtration. It's coming through. This is called a filtrate, whatever collects in here. It says that blood cells are not normally filtered. There should not be enough permeability here to where blood actually from this gets filtered. Just constituents that are dissolved in the plasma. That's the stuff that should get filtered through here. Proteins should not be filtered either. I don't know if that's up here or not, but your blood proteins should not. You shouldn't. When you test a person's urine, there should not be, and we'll do a urinalysis test to show you, but you should not get what's called an albumin test. Albumin is a protein, and that's just like a generic protein test for urine. There should be none or very low in terms of a protein test in urine. Those should not be crossing that barrier. Normally about 20% of the plasma is filtered, so you can see that it's not very efficient. It comes in fairly quickly. It's got a little bit of pressure behind it, but it kind of just moves in and out pretty quickly as well. So only 80% of it just kind of keeps on going and gets out here without ever being affected. Only about 20% actually gets filtered through this membrane right here. Now that means there's a lot to do then with this reabsorption, secretion, that kind of stuff, and that's what we're going to talk about. Now, the glomerular filtrate is produced at the rate of 125 milliliters per minute, which translates to about 180 liters per day. So that's what? 92-liter bottles a day of filtrate that your body processes. Now, we don't make that much urine. Otherwise, we wouldn't get anything done. Okay? So we're going to look in a minute as to how much of that actually turns into urine, but realize what gets filtered by the kidneys is that much, 180 liters per day. We put a strain on our kidneys. Okay? We use them a lot. It's a miracle they don't wear out faster than they actually do. And when we put other things in there, foreign compounds, a lot of medication, drugs, alcohol, you name it, caffeine. Look around, caffeine. We had to curb the Mountain Dew habit that my wife had, but she's finally over that. It's hard. It's hard on your kidneys. There's a lot of work that they have to go through on a daily basis. Okay, so I already talked about this, reabsorption and secretion. I told you where stuff is going where. You'll find that as we go here in the proximal convoluted tubule versus the loop of Henle versus the distal convoluted tubule, they become specialized at moving certain things. You'll find different levels of things being reabsorbed and secreted at various points along the nephron. That's where it gets a little complicated. Okay. So you need all three of these. What you see right here. This, the filtrate forming, what's pulled out of it and what's put back into it. All that put together is going to comprise what it is your urine's made of, what's in it. Okay. And then I was teaching another class. People were talking about washing hands before and after the bathroom, and people would use, and I don't understand, you guys probably know because you're in the health field, but these people were not. And we were having a discussion about washing your hands after using the restroom, and some people said that they didn't pee on themselves, so they see no need to wash their hands. But of course we know that most urine, that's not where your bacterial problems are. It's fairly sterile, right? I mean, this is, if you consider what's in it, there's not much that could live in it. Maybe along especially, like in the urethra towards the end and maybe through there, but a lot of that gets flushed anyways during the urination process. But anyway, it just reminded me of it. Just thinking. Urine itself is pretty clean, so to speak. It's just kind of, Yeah, right, that's what I'm saying. As it's going out and coming in contact with epithelials and all that kind of stuff, that's where it gets kind of gross. That's when you know you got a friend. Okay. And that one didn't make TV? I don't know. Oh, I don't watch that crap. So, but anyways. No, not everything. Just. Okay. Well, I mean, it got to the point with me now. It's like, God bless TiVo, first of all, because that's just awesome. Otherwise, I'd never watch anything. But it got to the point now where I used to be able to record everything and wait till the kids go to bed, and I could watch my stuff. But not now. Now I just got this whole list of stuff I've recorded I'm never ever going to get to watch. I just don't have time. So it's like 72 events. I got to flip through them all the time. I'm never going to watch them. Okay, now, we're going to look obviously more closely, as always. Got to get down into the cellular level about what's going on here. We look here, here's a glomerulus here, here's our Bowman's capsule. What we're going to look at is, at the cell level, what's happening. So if we zoom in, let's take a chunk out of this little capillary right here. You'll see this. Now what you need to realize is this yellow area around is actually the Bowman's capsule. Okay? These little sort of jagged things that are all locked together like puzzle pieces here wrapping around, those are called podocytes, or like foot cells. And they actually are connected. They are not part of the capillary. They are actually, they are touching and sort of part of the actual tissue out here that's sort of between the capillary and the Bowman's capsule out here, the actual nephron tissue. So these guys are sort of the junction between the capillary and this nephron tissue, okay, this Bowman's capsule in this case. So they're going to sort of hold everything together. They can become more and less permeable. So whenever you take a cross-section now, we're going to cut out part of the wall of this capillary and look at it over here. You'll see that we've cut, these are actually these cells right here, these sides of them that you're looking at right here. Okay? These are the podocytes that you see, these little things that look like teeth. Okay. Now, we've got to cross 3 barriers. So we've got a very selective process here. We've got up here, we've got the actual capillary, and if you take a look at these cells, what you'll notice is there are actually reasonably good-sized spaces between these cells up here. Like I said, these are more permeable cells than regular capillaries are. Okay, so you've got, number 1, the wall or lumen of the glomerular capillaries, which is this right here. There's a very, very fine, small space between that and the actual Bowman's capsule. The middle space is called the basement membrane. That's this right here. It's sort of a gelatinous, gooey sort of layer that connects them. And then lastly, we've got the inner layer of the Bowman's capsule, and that's these podocytes that you see here. Okay. Just keep that in mind. Now, I'll show you why these arrows are up here. It's sort of direction of pressure. If you can see these red arrows, they don't show up real well. But, now, realize what's going on here. There's a lot of pressure changes that are happening and that are controlling the drive behind this filtration process. First of all, you've just got pressure from the capillaries themselves. From the circulatory system, as it's pumping blood through here, there's a pressure within it. So that pressure is pushing outward against the walls of the capillary, trying to push stuff out of the capillaries. That's that pressure. And you're going to see that that's about 55 millimeters of mercury. That's a reasonable pressure in terms of bodily fluid. You think about, like I said, with the sphygmomanometer or your blood pressure cuff. 120 over 80, your diastolic's about 80 on average. So this is a little bit lower than that, which, considering that it's so far away and down in the kidneys and in a capillary region, that's not too bad. We've got reasonable pressure there. But realize you don't get all of that pressure. Okay? Otherwise, it would just blow out your capillaries is what would happen. There's opposing pressure that comes. You can always have pressure going in this direction and still have pressure coming back at it. It's a matter of if this is still bigger than this one, then you can get a net movement in this direction. If you pulled the resistance out of the way, you would just get a lot more. So that's what you're going to get here. There's going to be other pressures involved that are counteracting this. You're going to have about 55 millimeters of mercury just from pressure on the inside of that capillary pushing out. Okay. There's also, though, something called the plasma colloid osmotic pressure. Now remember, anytime you have anything dissolved in a solution, okay, and you've got a barrier between the inside and the outside of this thing, say a cell and its environment, the more stuff that you have dissolved inside of it, you're going to affect its osmotic gradient. The more solutes that are present, that means the less percentage of water. So water is going to come into there. So that's why we always say, like, think of sodium or whatever. Wherever sodium is, that's where the water is going to go as well because of the osmotic gradient. Okay, well, instead of using sodium, there's going to be a plasma colloid. That means these are going to be those little proteins that's constantly floating around in your blood. Colloid is a chemical word to describe, like, suspended particles. Okay, like mayonnaise is a good example of a colloid. It's sort of like a liquid/solid, sort of like just suspended particles all there. Can you imagine just eating a big jug of mayonnaise? That'd be disgusting. Anyways, that's like my daughter, my littlest one. She always eats butter. I can't stop. She gets it out of the refrigerator and just like takes a spoon and just eats butter. That's so disgusting. I mean, butter on things is fine, but just like spoonfuls of butter is just nasty. Next thing you know, she's going to be like taking vegetable oil and pouring it on her butter and then eating it too. Dipping it in soy.
She's going to be the one you're not going to be able to control.
It's gross. All right, now, here's what happens in the other direction. Notice my arrow. So I'm just going to say I'm moving this way, and these arrows just represent a pressure in the opposite direction, is all that's saying. So what you got to realize is as this stuff is being pushed through these capillaries, it's coming through the blood. Here's the Bowman's capsule. Here's the stuff coming into the glomerulus. The stuff gets pushed out, and you're starting to get filtrate over here. What's behind here now is more protein, a more concentrated form of the things that were dissolved in the blood because there's less water. As this stuff gets pushed through, things that are dissolved in water and water itself sort of gets pushed through, pulled out of that plasma. And what's left behind is still plenty of water, but realize less now because some of it got pulled out. And now some of it got pulled out, what remained were all those particles that were there to begin with. So what in effect that you have done is concentrated the blood plasma after it passed through there. So if you've concentrated the blood plasma, now you have an osmotic gradient that any water right around the outside, not involved with what's going on, now wants to move back in that direction. Does that make sense? You've got, like I said, first of all, you've got pressure coming into the capillaries. Okay? You've got a Bowman's capsule. That pressure in the capillaries is forcing stuff through that Bowman's capsule into the tubule. So here's a pretty high force. That's this one, the 50 millimeters of mercury. At the same time, as that stuff is being filtered through, remember that the plasma proteins, the red blood cells, all that kind of stuff stays behind. So the only stuff that's coming out of here is stuff that's water-based, and stuff that's dissolved in water. That's what's passing through here. Your suspended colloids, your plasma proteins, stay back here. So there for a while, what you have is the same level of plasma proteins, but now less water that it's dissolved in. So basically, you've made it more concentrated. By making it more concentrated and having a higher level of protein here than you have out here, the water behaves the same way. You set up an osmotic gradient. Now the water is going to want to rush back in. Okay? So when you've got water wanting to come back in, that's going to oppose the force that's trying to just, from blood pressure, pushing it through. Now what you're going to see is that the force from the osmotic force that's wanting to bring that water back in is not near as much as what's pushing it out. I should have a value here. Should be 30, yeah. About 30 millimeters of mercury. Okay? So that means there's still a difference of about, 25? There's still 25 millimeters of mercury difference, so you still got enough force to push that plasma out of that glomerulus, out into the Bowman's capsule. You just got a little offset coming in against it now. But what you'll also find is that there's another force pushing in against that. So now you're going to have even less than 25 millimeters of mercury pushing out. You've also got a hydrostatic pressure. Hydrostatic pressure has to do with standing water. Just like in a pool. The deeper you go, the more pressure you feel. So the more water present, the more it exerts a pressure just by being there. So it's sort of like a double whammy with this, because when this draws water in, the fact that you've drawn water in now creates a hydrostatic pressure. Okay? And it will oppose that which is coming out as well, right? The fact that you've pushed all that plasma through, okay? Now, the point is all of this is that when everything is balanced out, okay, you've got about 15 millimeters of mercury associated with this opposing pressure, 30 associated with this. When you're said and done, you end up with about 10. You end up, the force that actually pushes it through the capillaries ends up being about 10 millimeters of mercury. So that's certainly not too taxing. Okay? That's not going to blow a hole in the kidney anywhere. So that's where this math comes in. Okay? That's how you get this 10 left over. Okay, now, so the net filtration pressure is 10 millimeters of mercury. Much, much less than the blood pressure. All right, now, there's something called the GFR. That stands for glomerular filtration rate. Basically, how fast and how much you are filtering through the glomerulus at any given time. Okay, so it's going to be a volume per unit of time is a rate. Okay? Now there's a couple things that's going to affect this. Number one, this pressure right here. Realize that if everything's constant and this pressure increases, you're going to filter more. If that pressure drops, you're going to filter less. Okay? But think about everything else that could affect what's going on. Even if you keep this pressure the same at 10 millimeters of mercury, but somehow you can make your capillaries more permeable, guess what? You're going to filter even more. If you can get more surface area and include more capillaries, you're going to filter even more. And the opposite is true. You shut off capillaries, don't use them. Put the cells closer together, lock up your pores more. That's going to decrease all the filtration rate. So that's what this is saying. There's going to be several things that are involved in controlling how much you filter through there at any given time. The pressure is just one of those factors. You've also got surface area and permeability of the actual membrane. Okay, so there's a lot. Nephrology would be a really hard thing, I would think. If you watch House, he's got a double specialty, one in something about diagnosis of the Netherlands and nephrology. If I was a doctor, that's what I would be. I'd be that guy. I wouldn't be near as smart as him. I'm just saying that's how I would deal with people. just short, smart alecky, everybody's dumb. I don't know. Yeah, but I would never be right like him, and I would never have that many good points, but I would try to pull it off anyway. My wife was telling me a recent news story. Some guy from Harvard Medical School was being interviewed. I don't know if it was on 60 Minutes or what. It's what he was, and they were talking about how ridiculous it's become. And sometimes doctors, like, if they don't like your voice, they won't even listen to what you're saying. They just go through their checklist and they do what they want. And they try to hurry up and get out of there. Well, it ended up being that he ended up killing a patient doing that. And he couldn't stand her. He said that she had this annoying, high-pitched voice. Couldn't stand it. It was like fingernails on a chalkboard. So he'd get in, get out, get in, get out. He didn't want to talk to her anymore. She ended up dying of a heart attack. And when he went back and reviewed things, he could have done something about it. I mean, it was at that stage. And then he felt bad. He told the family, and he said, I realized he wasn't trying to get out of anything. He was just apologizing. They ended up not suing him, I think basically because he apologized. But now his mission is to teach those people in medical school and go to the other doctors and try to change things as opposed to just keeping it in practice now. But yeah, I know. I mean, and I hate that. You go in there and it's like you're nobody. You're just a number. And they go. It's like a car mechanic. That's what it's become like. They go through and they'll check this and put this piece in. If it don't work, come back and we'll put another piece in. We'll just troubleshoot at default as opposed to do the right thing. We're not dealing with cars here. We're dealing with people. But and that's what it's getting to, though. I mean, for those of you who know anything about, I don't know, your husbands or you or whoever know anything about vehicles, and like I used to have an '88 Ranger that I could sit in and I could still work on. I had room to work on. Now everything's so digitized and technological. Some of the things are cool, but you can't work on anything yourself. And instead of learning about the mechanics and how all the engineering works and how a car works, they become fewer and fewer people like that, and more people just to know how to run the machine that tests your machine. You've got technicians that are trained not to think, but just how to push buttons and know the sequence of events to program. And I'm afraid if we're not careful, this is what our doctors are going to become. They're going to be highly specialized people that know how to call for certain tests, and that's it. And they're going to lose that creative ability to think and to diagnose and to come up with these things. And we're well on our way to do that. You're getting a bunch of mechanics is what we're going to end up cranking out. And that's not necessarily a fault of their own. Insurance companies are going to drive that as well. They have a huge role in that because you don't get paid unless those insurance companies agree with what you're doing. So. Yeah. If you're looking for an argument, you're not going to find one here. Okay. Now, as far as how we can control, what if our body senses that we need to readjust and we need to control our filtration rate? How do we do that? There are autoregulatory mechanisms, in other words, things that are inherent within the kidney itself it'll respond to, And then there are, of course, overriding signals that come from a greater place. Our brain, our neural signals, that kind of thing can come in and override that. It just depends. So first one is autoregulation. There are sensors that can just adjust dilation and constriction of the arterioles, the tiny little arterioles that are feeding into this glomerulus. For example, if blood pressure gets really high, what our body can do, realize that if blood pressure is high and our body didn't do anything about it in terms of our kidneys, that would just increase our filtration rate. It would push stuff through more. So what our kidneys do, they have local control mechanisms. They can shut this, they can cause a constriction of these arterioles and minimize, if our body, our total peripheral blood pressure increases, what it will do is pinch shut and reduce the amount of blood coming into the kidney. Now that may seem counterintuitive, but realize that by reducing the amount of blood coming into that glomerulus, that's going to reduce the pressure. It's going to slow down the filtration rate. Okay? It's not bringing in as much blood at one time, and we can control that a little bit better. Now, if our total body blood pressure drops, what you will see is the filtration rate would normally drop. So what our kidneys do then is, where the rest of our body would constrict, right, to increase blood pressure, what the kidneys will do, only in the little arterioles that are feeding into this glomerulus, they will dilate. Because the rest of the body has tried to increase the blood pressure. And you've got to realize the function of the kidney. The function of the kidney is to get blood to push through it, right, and filter it out. So if the whole body has dropped in blood pressure, the kidney has to not drop its filtration rate. So what it will do is dilate. It will open up so that more blood can pass through that glomerulus to try to maintain a constant filtration rate. Okay? Sort of the opposite of what the normal body would do, okay, the rest of the body. All right, that's basically all of this, what this says. So. Okay, now like I said, we can override this. We could have sympathetic activity from our nervous system, from our autonomic nervous system, come in, shoot some impulses, and say, I'm controlling this at a higher level. Okay, we need to increase this, we need to decrease this based upon inputs that I've received from other places, not just what's going on there at the kidney. Okay, so that's that's all of this. Now, the baroreceptor reflex is our little, just like in the circulatory system, little sensors that can sense that and feed it can mechanically be stretched if the pressure is too big or whatever. It can send an impulse to the nervous center, to the nervous system. It can come back and cause relaxation, dilation, whatever, in accordance to that. So that's, we've still got baroreceptors that are going to play a role in kidney vasoconstriction and dilation as well. Okay, it says here that the afferent arterioles, the ones feeding into the glomerulus, constrict by sympathetic innervation. So if there needs to be some sort of reason that they need to constrict and slow down the filtration rate, sympathetic stimulation will do that. Okay? Realize what that'll do too. It lowers the blood pressure in those capillaries. This does not lower total blood pressure. As a matter of fact, this group we didn't get to talk about the blood vessels. But what would happen is sympathetic stimulation, body-wide, constricts your blood vessels and it increases your increases your blood pressure. But realize when I say what's going on here, when you get sympathetic innervation to this particular region and you constrict these blood vessels that are going to the glomerulus, realize that it actually lowers the blood pressure going into them. Okay? It lowers the amount of pressure that's going in to be filtered, is what that means. Like I said, this is opposite of what's going on in the rest of the body. So, okay, well, anyways, if you can decrease the filtration rate, you're going to reduce the amount of volume of urine formed. It'll help you conserve plasma volume. It'll end up increasing total blood pressure throughout the body. It's just like water, the water that goes in with urine. The more water, the more dilute the urine. The more you're pulling out of the body, you're going to use that to help decrease blood pressure. The more water you put back in, the more water gets stuck back in the bloodstream, and the higher the pressure associated with the body, blood pressure. Okay. All right, now taking a look, this picture again. Remember, this is where they would cross. This is where the cross would happen from the capillaries, cross those membranes into the nephron. Okay? In this case, the actual Bowman's capsule part of the I mentioned the word filtration coefficient, and that is a number that sort of is all-encompassing to describe everything that's going on to determine how well something is going to filter. Sort of like we talked about diffusion coefficient with oxygen and carbon dioxide. Some gases are just normally better at diffusing than others because of the interaction they have with one another. In the case of carbon dioxide and oxygen, because of the affinity they have with hemoglobin. There's a lot of extrinsic factors that could end up playing in as to how well something diffuses. In this case, we're talking about how well something filters. So again, we've got what's called a filtration coefficient. It's sort of all-encompassing. So we've got surface area to deal with. The bottom line is it's not constant. There's a lot of ways we can change the filtration coefficient and thus change filtration. You know, if we're dealing with cells and tissues and bloodstream and all kinds of stuff, there's all kinds of things that our body can do to change that and to affect it. Surface area, permeability of the membranes, all of this can be adjusted, changed. And that's the value of this coefficient can change as a result of that. You can take what's called mesangial cells and sort of pinch off little various places on the capillaries. You can reduce the amount of capillaries being used at any given time, just like in the body. Well, we can do that in the kidneys as well. If you do that, you obviously, since you're using fewer capillaries, you're reducing the surface area. Now you've got less space over which to filtrate. That's going to slow some things down. These podocytes that are surrounding this area right here, they can come closer together. They can tighten up. They can relax. They can thus decrease or increase the number of filtration sites available. If they close up real tight, like where that number 3 is right there, if they close up or some of them close up or whatever, you're again reducing surface area. You're not allowing as much space for this stuff to pass through. So that can affect it. It says here that the kidneys receive almost a quarter of the total blood supply. That's as it's directed towards the body. Of all the cardiac output, about a quarter of it, up to a quarter of it anyways, can be found in the kidneys. Now realize why. It's not because necessarily the kidneys are so high maintenance, because they need all that oxygen and transportation away of the carbon dioxide. It's because they are a reconditioning organ. That's their job. Their job is to handle a lot of blood and fix the levels of stuff in the blood. So that's why they receive this disproportionate amount of blood to them at any given time. Okay? Obviously, part of it's to nourish the kidney, but most of it is not. So, renal blood flow is about a little over a liter per minute. So there's a lot of blood that's passing through our kidneys. All right. Now, I talked about, I mentioned tubular reabsorption. I mentioned tubular secretion. Now we're going to look at the mechanisms that control that. So, well, again, reabsorption, we're going from the lumen of the nephron into the capillary. Now, selective and variable. Variable means it has a wide range of possibilities. It has a wide range of, well, for example, you can increase the amount of stuff going across at any given time. You can decrease it. It's very variable in that sense. However, just because it's variable does not mean that it's not highly selective and it's not highly controlled. It's a controlled variation. Okay? That's what's important to understand. Now, in order to maintain our extracellular, our tissue fluid, our normal balances throughout our body, we've got to be able to return substances to the blood when we need to, given certain situations, and we've got to be able to pull stuff out of that blood into our waste when we need to, if it didn't get filtered. You'll see that some things never actually make it through. Creatine, I mentioned that back when we talked about muscles. A lot of drugs, waste products and that kind of stuff don't ever get filtered through that glomerulus. And if it wasn't for all this kind of stuff, they would never even get pulled out of our blood supply. So this is a very important phenomenon here. So after, what happens is you get a bulk filtration. It's sort of like, you get all the crap that doesn't matter in terms of the biggest chunk of stuff out of the way right at the beginning. Not that it doesn't matter, obviously everything matters, but you get a big load of stuff out of the way right at the very beginning by trying to do this filtration. And then what's left, then you can control. You can monitor and you can say, okay, I need to actually pull out a little bit more sodium, so I'm going to pull some out. Or I need to bring in some hydrogen, so I'm going to pull some out of the bloodstream and bring it back in. This is where all that's going to happen. Only excesses of materials end up being eliminated as a result. It's a very efficient process. We don't waste any more than we have to. Okay, reabsorption rates are high. Now remember what I mean by reabsorption. I'm talking about from the tube into the bloodstream. We reabsorb a ton of the stuff that actually gets pushed through that filtration process. Remember I said 125 milliliters per minute is actually what we end up filtering. That's the filtrate, the amount of filtrate that forms. Out of that 125 milliliters of stuff that collects in your tube, 124 milliliters of it is reabsorbed. So that leaves only about a milliliter every minute of actual waste that we are producing. That seems a lot more reasonable when you consider how often we go to the restroom. Okay? Notice that there's a lot of water in the blood plasma that passes through that glomerulus into that filtrate. Okay, it's mostly water, matter of fact. Notice that about 99% of it gets reabsorbed. Only about 1% of the water that passes through actually stays in and becomes part of waste. So that means you realize how much water actually is in urine, and you start realizing how much water must be in our body and circulating around at any given time. So 99% of that water is reabsorbed. Glucose is 100% reabsorbed. You will see that glucose makes it through the Bowman's capsule, gets pushed out, and gets collected in the nephron. But you will also notice that almost immediately what starts to happen is it gets pulled back out. There are mechanisms that extract that glucose back out and put it back into the bloodstream. And for most of us, I don't know who's diabetic, who's not, but if you're not diabetic, then 100% of that glucose should be pulled out. Now, in some people, that will not happen, and I'll explain why a little bit later. It mostly has to do with the sheer amount of glucose present that their body is not taking into their cells, and it reaches its threshold, it ends up spilling over into the urine. I'll explain that in a minute. Okay, so glucose should be reabsorbed. There shouldn't be and as a result, that's why it's abnormal. If you test for glucose in the urine and you see the presence of sugars in the urine, or glucose in the urine, or whatever, you know that something's wrong, because our body is designed to pull all of it out. All right, 99.5% for salt. Of all the salt, when I say salt, I mean, of course, ions like sodium, potassium, chloride ions, that kind of stuff. Those salts should all be pulled back out, almost all of them, because we use them in our body, in our cells, everywhere. But only a small amount actually end up staying in with waste. Okay. Obviously, those numbers, like salt can vary. If we just eat like 5 pounds of salt, that number is going to change, obviously. But that's average. Okay, what? What's the point? What do you mean? Oh, okay. Well, what you get with a lot of those kind of things, like with fresh vegetables and with these energy drinks, it's a lot of things called antioxidants, and you'll hear that a lot. And it's supposed to, they'll claim that it helps with the flu and cold, and drink vitamin C and antioxidants and all this kind of stuff. Where your antioxidants are going to combat, they're going to combat things called oxidized free radicals. You'll probably hear that word in the midst of all that too. And where this all comes from is, well, a great place is where it comes from is think back all the way to like one of the first chapters we studied. We talked about the electron transport chain and how oxygen at the end accepts the final electron. Okay. Well, sometimes that electron gets accepted by things that aren't good. Sometimes that oxygen ends up getting supercharged and reacts with things. What we showed up on the board was a perfect situation, and what usually happens. Sometimes you get free radicals. You get extra charged things that float around and start destroying tissue. And what antioxidants can do, and how you can cleanse your body or whatever, is you can take things that naturally want to react with a lot of these oxidized molecules. That's why they're called antioxidants. They go in and they help neutralize some of that, and then you slow down any destruction that they may actually cause. That's the sort of the theoretical basis. You'll not find that there's too much approved medical stuff with this. It's not like FDA approved stuff. It's this stuff that you see on the commercials. The theory behind it certainly works. It's sort of like when we talk with cortisol. You could take cortisol and you could lose weight, no doubt about it, because you're going to mobilize your energy sources. You're going to put those things, you're going to break down proteins, you're going to break down your fat stores, but at what cost? Obviously, the risks may not outweigh the benefits since it's not been approved by medical professionals. you lower your immune system, you increase your rate for acidosis, you put more ketones in your body, all that kind of stuff from doing this. So, I mean, you just have to weigh the pros and the cons. I mean, research it, find out exactly what the chemical is you're talking about, what it's claiming it's able to do. And most people, you'll realize that the people who are selling it don't really know. I had I've tried to leave names out of it. I've recently been discussing but I was recently discussing a guy who claimed to be a doctor up in this state, northern Indiana, and he's alternative medicine, and he sells supplements, herbal things, and things like that. And some people who I know very well, be it family, friend, whoever, were considering buying his product and was sort of buying into it all. And I'm not saying it's wrong. I'm just saying I'd like to know more about it. So I contacted this guy, and I said, please tell me your credentials. Where did you study? What is it that you've studied? What is it you're claiming? And why does this stuff work? And, it basically I didn't get anything out of it. He got some kind of degree from some kind of place. I don't even know what it was. But it was all this, this herbal medicine kind of things like that. And what you get with this kind of stuff is the studies that they will not know half the time chemically and medicinally how this stuff works. All they will quote you and what you will find are case studies saying, here's some people who took it, it shows that in this many % of the cases it works. And that's the research they go off of. Whereas in hard medicine, they go off the pathways by which this stuff works. Like if you know how a drug works when you take it for the most part. Otherwise it doesn't pass FDA approval. They know the mechanism by which it works, and they can tell you it works, like penicillin works to destroy bacterial cell walls. With half this stuff, you can't. All you can say is, I don't know, it's been around for thousands of years, and the Chinese people have used it. I'm not saying it doesn't work. I'm just saying it's a whole different type of approach to the research and a whole different approach of acceptance, I suppose, when the person takes it. Right. Well, and they don't have to be, because a lot of times they call it natural, right? They call it natural stuff. The reason they don't have to be is because they use chemicals that are present in things. They're not natural. They make pills. They're made in a factory. They compress this stuff. They synthesize half these materials. And they make all these chemicals themselves in a chemical lab, put it into pill form, and claim that it's natural. And the reason that it's natural is because that same chemical can be found in a plant elsewhere, somewhere in the world. And as long as you can make that claim, then technically the FDA can't regulate what plants you eat, and they can't regulate what drinks you drink, from a natural setting. So that's why they don't have all these regulations. So it's not really natural. There's not this greenhouse out back, and they're taking these little leaves and grinding them up. Some places do, I guess. But like when you order this stuff from TV or whatever, there's no little lady out back, just making this nice fancy tea. And it doesn't work like that. It's just this crap. It's all compressed and put together. And the fact that it's not synthesized in a laboratory, like when you get to Eli Lilly and you get to Pfizer, and the drugs that are there, they are manipulated. They react with certain things, and they form new chemicals, and they form new drugs. That's it. And they put it together, and it's synthesized. When you do that, and it doesn't exist in nature, there's a lot of approval you've got to go through to say that it works or it doesn't work, and it's safe for human. When you just take a chemical that's already present on Earth that can be found elsewhere, you don't have to do that as much. So that's the difference. All right. Keep in mind what we got going on here. Take this picture, keep it in your head, know the parts, and then we're going to talk about these. Okay. I'm going to skip all those words and show you with a picture. Okay. Here's what we got. Here's our Bowman's capsule right here. Here's our glomerulus. Here's our filtrate forming in here. What we're looking at is what barriers must this stuff cross to get into the bloodstream. And here's what you're looking at. Here's the luminal membrane. In other words, here's the inside of this here tube. Notice that the cells are single layered. There's one layer of cells, so this is very thin. Tight junctions between the cells. Stuff doesn't leak through here. It's highly controlled as a result, because if anything's going to pass from one side to the other, it's got to pass through the membrane. And the only way stuff can get through the membrane is either it dissolves, or it's got to have a specific protein channel that's going to operate with it and help it cross. So what you'll find is, in the luminal membrane, stuff has to cross over, and then you'll find there's a lot of regulatory stuff happens right here on what's called the basolateral membrane. There's like a sodium pump and a sodium-potassium pumps through here. There's other stuff that's happening that is going to regulate what comes in and out of this particular cell. Okay? And that's what this shows up here. Notice where it's all in reference to one another. You've got plasma over here. You've got a lateral space here. There's going to be an accumulation of stuff in here. And what you'll see, the point of what happens is sodium, for example, is going to be in higher concentration in here. It will move in. And we'll get into this cell. In order to get something into the plasma, what the most efficient thing to do is to get it into the bloodstream is to create a huge pool of it right out here. If we can create a whole bunch of sodium, for example, right out here, we can cause it to just naturally diffuse into the blood here. So what you'll see is along these basolateral membranes right here is sodium-potassium pumps that are going to crank out, and remember I said shutting, like cramming the closet door shut, trying to load stuff up. You're going to be loading up sodium out into this area and keeping it from backwashing because it won't be permeable back in this direction. The pump will only force it in this direction. Load it up out here, and then it wants to diffuse in there very easily. That's what you'll see happen. And the opposite will be true for potassium. Remember, they always go opposite places, sodium and potassium. Yes. That's right. What you will see is with an increase in sodium in the body, you'll see a decrease. Should be maybe not direct proportion because there's like a 2 to 3 kind of thing going on. But you'll see some potassium move out from here, cross in here, get pumped in here, and then go back into the filtrate if sodium goes out. That's right. Okay. Now, you'll see that there's passive and active reabsorption. It depends on whether or not energy is being used. Sodium is going to be active, and I told you that there's going to be a pump there. About 80% of the kidney energy is spent moving the sodium out of these cells. So sodium is a pretty important element to our body. 67% of the sodium movement occurs in the proximal tubule. Remember where that's at. Okay, right after the glomerulus, right after that Bowman's capsule, that interface. So a lot of it happens right up front. Okay. Now, the reabsorption of glucose, remember, taking stuff back into the blood, pulling it out of the tubule back into the blood. We've got glucose doing that, amino acids, water, chloride ions, urea. All of this is linked to the movement of the movement of sodium. Rather than trying to use a fuel, ATP, to create pumps for all of this stuff, we do it for sodium. And then it sets up gradients that allows all this stuff to sort of hitch a ride from that energy. Okay, so all this stuff is going to move by what's called secondary active transport. And this stuff is going to move as a result of sodium moving. Okay, that's pretty much all you need to know about it. Chloride is going to move because it's negatively charged and attracted to sodium. So wherever sodium goes, it sort of follows. Okay? These other things just move because of the gradient that movement of sodium produces. Okay? All right. Now, the reabsorption in the loop of Henle. Whatever's left, then we can still absorb more, pull more sodium out. We haven't pulled it all out. We can pull out more. But you'll see is once we get past the proximal tubule, we get down to the loop of Henle and the distal tubule, it becomes more controlled. There are more external factors that need to feed in to tell you how much you need to pull out and that kind of stuff. Hormones, nervous system, you name it. Okay. So there's more control here. It's not a bulk removal like you had up with the proximal tube. This is a bulk removal of sodium to get just a bunch of it out of the way, and then you have a workable amount. You're done. The distal tubule, you'll find that in the distal tubule, right before, especially even in the collecting duct, but especially in the distal tubule, there's going to be hormonal control that's very important. You're going to have hormones that are released, and we'll talk about that in the endocrinology chapter. Hormones will be released that will tell your kidneys to pull in or let go of more sodium. And that will ultimately be involved with controlling your blood pressure. Maybe you've heard of like vasopressin, ADH. Some of the diuretics and the antidiuretics that are prescribed and that kind of stuff, some of them work on a hormonal basis. ADH stands for antidiuretic hormone. It's produced in the hypothalamus, stored in the anterior or posterior pituitary. But we'll talk about all that later. Well, I'm getting there.
Oh.
It'll be up here. Okay. Let's see what I got to... Oh, I already talked about this. There's going to be a sodium-potassium pump moving this stuff. Let's see. Already talked about this. Talked about the co-transport stuff already. Hormonal control. I think I talked all about that. So let's look at this picture. Okay. Yep, we have to. Now, if you look at this, this is what I've sort of already told you. If you have sodium that's pushed through and dissolved in that plasma as it pushes through that glomerulus out into the Bowman's capsule, it starts to become filtrate. There's a lot of sodium in here. So sodium, there's a concentration gradient that's higher out here, lower in here. So sodium wants to go through these channels and diffuse in. Now, when it diffuses in, what you got to realize is what's going on because of everything else in the body. There's a ton of sodium buildup right out here. So what's not going to happen, it's not going to just diffuse in and then diffuse out. Okay? This is sort of like a one-way valve out here. Sodium can go out, but sodium can't come back in. Okay? So what has to, because there's so much out here, if there wasn't control mechanisms right here on this basolateral membrane, if there wasn't something keeping that sodium from coming in, it would all flood right back in. You'd be back where you started. There's got to be something separating this and keeping the sodium out here. So the only way sodium can cross this is through this sodium-potassium pump right here. We've already discussed all that, how it works, back in previous chapters. But realize that with ATP, we can spin that. We can spin a sodium around, and in turn, we have to move potassium. So potassium comes in. So we use the same pump, the same energy, to move sodium and potassium, okay, in opposite directions. So we spin sodium out here, and we load this up, and we get a high concentration gradient of sodium out here, and then it easily diffuses back into the blood right where we want it to go. Okay? Now, what you will see is if we need to get sodium out of the blood, we don't have anything that really works in the opposite direction, but what we will do is slow all of this down. Okay? So when you slow this down, and this stops working, some of these can close up or whatever, what you will see is not near as much sodium can go in, and that basically has the same effect as bringing some out. Okay, so that's, well, we'll get in. I'll discuss those, and that hopefully make more sense. I'll show you where they can target that. If you take what you should take, after you've completed this class, I got a good class that you should take. The problem is it doesn't count for anything. Well, if you get your MSN or your family practitioner, nurse practitioner, or whatever. My wife took the class at ISU, and there was a bunch of those people in it. But it's an advanced pathophysiology. It's a lot of this stuff, but it applies it specifically to certain diseases and things you would find in a clinical setting. You guys would benefit a lot from it, I think. Talks about a lot of the drugs and what's used now to treat some of these conditions. Like when you talk about nephrology, this kind of stuff, talks about what patients are likely to present you with, what are you most commonly going to see in this situation, what drugs are out there right now being prescribed for that kind of stuff. It's really interesting. But, it's online, too. That's why I was going to say you could take it. You don't have to go to class. You could. Come on, you can do it. Okay, hang on. Let me